So greetings. So welcome to today's class. So if we recall in the last class, we just started off with steering dynamics, fluid dynamics, and then we looked at the Ackermann steering geometry, which forms the basis of the steering being done in most road vehicles today, and the the idea behind that and the corresponding steering Ackermann steering condition, right, which provided a constraint on the various variables. So in today's class, let's look at one realization of a steering mechanism that could be used to achieve this Ackermann steering geometry. So we are going to look at a trapezoidal steering mechanism or a four-link steering mechanism, which essentially could be used to realize that condition, and then we'll derive an expression for this mechanism that will once again provide a constraint between various parameters involved in this mechanism, and then we'll see whether it helps us in meeting this Ackermann steering condition. Okay. So what is this trapezoidal steering mechanism? Let's say we consider the front wheels that are steered. So what we have is we have these three central mechanisms, right? So let's say we have these central mechanism, right? So which one could essentially view it, for example, like a central mechanism that connects these two rods together, right? So these two mechanisms are attached to the steering knuckle on the steering wheel, and there are two main parameters that essentially characterize the steering mechanism. So D and beta. So what is this D? D is the steering, so-called steering offset arm length, okay, which is the distance of these two arms that we can see. And then beta is the angle made by these arms, right, with the central plane of the steered wheel on either side. Okay, so those are the two parameters. Okay, and as we know, W is going to be the track of the vehicle, and essentially this left sub figure that is indicated here shows the arrangement of the steering mechanism when the steering wheel is centered. Okay, so there is no steering input that is given. All right. Okay. So now, if we look at this particular, steering mechanism, let's say, and we assume that without laws of generality, it is turned to the left. Okay. So we have this steering angle delta I and delta naught, which come over, and we can see how the steering mechanism is deformed, right? So we have these 3 points, X, Y, Z, that form a right angle triangle, like XZ be indicating the central link, okay, which connects the two offset arms. Okay, so let me mark the same XZ here. So XZ is going to be this arm. Okay, now the point is the following, right? Let's say we have this deformed position as shown in the right. How are the various parameters related to each other, and how do we get a relationship? Okay, so let's try to derive an expression for the same. Okay, so in order to do that, let us essentially mark a few points. Let's say we call this point as A and this point as B. Okay, so the distance, let me call this point as point C, sorry about that. Okay, this point as C, and the distance AC is going to be W. Okay, now what is the point B that I want to mark? If I draw a line which is perpendicular to this YZ, okay, the place where it intersects it is what is called as B. Okay, so that is my point B. Okay, and what I do is that I essentially draw a line which is perpendicular to YZ from point C, the point at which it intersects the extended line segment YZ, let me call it as point E. And if I draw a line parallel to it from X, the point where it intersects, let me call it as point E. Okay, so I'm just constructing some points, right, which are going to be our focus points. Okay, so as we can observe, this XYZ is a right angle triangle, and if we recall the Pythagoras theorem, and apply right angle triangle XYZ, we are going to have XY square plus YZ square. That is going to be equal to XZ square. Okay, so that is the relationship between the three sides of this right angle triangle XYZ. Okay, so now let's try to derive some equivalent expressions between the various like geometries that are found in this mechanism. Okay, so to begin with, if I were to ask the question, what is XZ? Okay, like in terms of the parameters that are appearing in this mechanism, let us first concentrate on the left subfigure. Okay, so suppose I consider this right angle triangle. Okay, so which I have just drawn. Okay, so the hypotenuse is d, this angle is beta. So we immediately know that this side is going to be equal to d sine beta. Okay, so because sine beta is going to be the opposite side by hypotenuse. Okay, so this side which is opposite to the angle beta is going to be d sine beta. Similarly, we can construct on the other end. Okay, and we can immediately write down that this side, this hypotenuse also is d. This is a right angle triangle, so this is also d sine beta. So immediately we can see that the expression for xz is going to be equal to w minus 2d sine. Okay, so these are rigid links. So we the lengths of these line segments are going to be constant, right? Even if they are deformed. So we have obtained an expression for xz. Okay, so what is this xz? Xz is going to be equal to w minus 2d sine beta. I hope it is clear how we got this expression. Okay, so and the way we got this expression was from the left subfigure. Okay, on this page. All right, so that's what we have got it. Now we have got an expression for xz. We need to now get expressions for xy and yz. How do we do that? Okay, in order to do that, let's now look at the right subfigure. Okay, on this side. Okay, so if we look at this angle, okay, sorry, if you look at this included angle, so this is going to be equal to delta I plus beta. Okay, so delta I is the steering angle of the inner wheel, and the beta is the design parameter, right? So it is the angle made by the offset arm with the central wheel. Okay, so that is delta I plus beta, and this angle, okay, is going to be equal to delta naught minus beta. Okay, so I'm sure we can easily identify how we got these expressions. Okay, so this is delta I plus beta and delta naught. Okay, which angle is delta I plus beta? The angle BCX. Okay, and the angle BAZ is going to be equal to delta naught. Okay, so that's something which all of us can easily figure out. Now we can immediately see that the side dx and ey, okay, are going to be same, and this is going to be equal to d sine delta I plus beta. Okay, because this hypotenuse is d. Okay, the arm length is anyway d, constant, right? So we essentially once again take this right angle triangle, let's say CDX, right? And dx is going to be d sine delta I plus beta. Similarly, this length, okay, which is CD, okay, is going to be d cos delta I plus beta, right? So I'm sure all of us can immediately identify these lengths. Okay, basic geometry. Okay, we are not doing anything, right? Then this length, if you come to the right side, okay, this length AB, okay, is going to be equal to d cos delta naught minus beta. Okay, so this length AB is going to be d cos delta naught minus beta, and this side dz, okay, is going to be equal to d sine delta naught minus beta. Okay, so just a similar arguments. Okay, so now we are almost set. Okay, so we have derived expressions for various critical lengths in this figure, and we are ready to derive expressions for x, y, and z. So what is x, y? X, y is this length. Okay, so we can immediately figure out that x, y can be written as AB minus CD, right? I'm sure all of us can immediately figure out, right? So xy is this length, okay? Xy is going to be the length of the line segment AB minus the length of the line segment CD, right? So that's pretty straightforward. And we already know AB and CD, right? What is AB? AB is going to be d cos delta naught minus beta, and CD is going to be d cos delta I plus. Okay, so that's what we have. All right. Okay. So that is xy. Now, what about YZ? YZ is then this distance, right? This is point Y, this is point Z, okay? So how can I get YZ? I can get YZ as CA, okay, which is also equal to EB, okay? CA and EB are the same, okay? They are essentially parallel line segments of the same length. And then from CA or EB, let's say I subtract EY and add BZ. Okay, so I will get YZ, right? Is it not? So CA is going to be W. I subtract EY, which is going to be D sine delta I plus. Then I add BZ, which is going to be D sine delta naught minus. Okay, so I have got the expression for YZ. Okay, so this is what we have been able to. Now we are going to use this expression for the Pythagoras theorem for the right triangle delta, XY. Okay, so as we already know, the expression for the applying the Pythagoras theorem to the right angle triangle XYZ, we get XY squared plus YZ squared is equal to XZ squared. Okay, so substituting for these numbers, so what will be xy? Xy is going to be d cos delta naught minus beta minus d cos I plus beta, okay, whole square, plus yz is going to be equal to w minus d sine delta I plus beta plus d sine delta naught minus beta whole square. Okay, and that's going to be equal to xz squared. Xz squared is going to be equal to w minus 2d sine beta whole square. All right. So this is an expression that provides a constraint between various parameters involved in this process, right? Starting from delta I, delta naught, which are the steering wheel angles of the inner and outer wheels respectively, and involving the track width W and the steering offset arm length D, and the angle that the arm makes with the central wheel plane beta. Okay, so this is what it is. All right. So now the question is, how do we use this, right? So before we discuss that, any questions on this derivation? Like what we did. Once again, what is the question that we started off with? We learned about the Ackermann steering condition. The question that we are asking ourselves is that we essentially want to figure out, how we can achieve it in practice, right? So we consider the steering, trapezoidal steering mechanism, whose design parameters are d and beta, right? So, and we got this expression that provides a constraint on the design parameters. Okay, fine. Any questions?
Sir, do we have any relation between del I and del O angle?
Okay, good. So we want as an additional constraint delta naught and delta I to satisfy the Ackermann steering condition. Okay, so we will come to that shortly. All right, so we already derived it. So if you recall, what was our Ackermann steering condition? Chord delta naught minus chord delta I equals W by M, right? Is it not? Okay. Ideally, we want delta naught and delta I to follow that relationship. Okay, so we will see whether we are able to achieve. Okay, good point. Okay, please recall Ackermann, let me write it on the side. The Ackermann steering condition was chord delta naught minus chord delta I was equal to W by L. Okay, that is the Ackermann steering. Okay, please remember this. Okay, yeah. Any other questions?
Sir, is this the only steering mechanism which is available?
No, not really, right? We have 6-link mechanisms also. Okay, so yeah. So in fact, I will give you a reference, after the class where you can look at more analysis also. Okay, I'm only considering a trapezoidal mechanism, which is a 4-link mechanism to begin with. Okay, yeah. Okay, so just so that we get a flavor of the analysis, and also we understand the challenges that are there. Okay, so we will understand the challenge when you do this optional exercise. Okay, so before I go and state what I expect you to do, any further questions? So what is this optional exercise that I'm asking you to do, right? So this is going to be a numerical exercise, right? So let's say we consider L to be 3 meters. Okay, so the V base to be 3 meters, and let's say the track to be 1.3 meters. Okay, so this is some vehicle. Okay, so which has these parameters. And let us say the offset arm length has been given. See, there are 2 parameters, it becomes very difficult to, we have only one equation, right? As we can see above, right? It becomes very difficult to solve for 2 parameters using one equation, right? So let's say we fix the offset arm length for the time being. Okay, let's say the offset arm length D is fixed to be 0.3. All right. So now what we are given is that we are given that the inner wheel angle has to be varied in the range of 0 to 40 degrees. Okay. So, and we want to figure out this parameter beta, which will ensure that both the above constraints will be satisfied. What are the 2 constraints? Constraint number 1 is this constraint of the trapezoidal steering mechanism. Constraint number 2 is the Ackermann steering. Okay, so essentially we are told that the inner wheel has to be rotated or turned up to 40 degrees. Okay, so this is a requirement which we are doing. Okay, now what is our task? Task is, question is, find the best possible value of beta that satisfies both 1 and 2. Okay, so we'll see that we are not going to be in a position to satisfy both at the same time always, but this is our expectation. Okay, so let's see how to do. Okay, so I hope the way it has been set up is clear, right? Okay, fine. Okay. Now, as I told you, this is going to be a numerical exercise. Okay, that is why I'm giving it to you as an optional exercise. Let us say, we are given a constraint. Let's say that beta is between 5 degrees to 30 degrees. Let's say, we are given this as a design input. All right. So what we do is the following. right? First, start with beta equals 5. Okay, 5 degrees. Now, what you do is, let's say you fix beta, let's say we fix beta to be 5. We have delta I in degrees. Okay, going from 1, 2, 3, all the way till 40. Okay, let's discretize in intervals of 1 degrees. Okay, so I'm just saying you can go for a finer discretization too. Okay, and just illustrate it. As I said, this is going to be a numerical exercise. Okay, we can solve it analytically. All right, so I'm only explaining the process. Then once this is fixed, we have to go and get, let's say, delta O from the Ackermann steering condition. So this is a one-time exercise for a fixed, what to say, a vehicle, right? So what we do is that, like, we essentially use equation 2. Okay, use equation 2 for this. Okay, and then we get the delta O. So what do I mean by delta O Ackermann? We solve this equation, right? We solve this Ackermann steering condition, and whatever delta naught that comes from that is our delta naught Ackermann. So for every delta I, we will calculate some value, right? This is a one-time process. Okay. Then what we do is that we calculate something called delta naught trapezoidal. So what is this delta naught trapezoidal? We go back to this equation. Okay, and then we use equation number 2, this equation, to calculate this delta naught trapezoidal. Okay, once again, easier said than done. That's why we are essentially using going to use a numerical method, right? So this, to calculate delta naught trapezoidal, we use equation number 1. We can see that it's an implicit nonlinear equation, right? So we have to do a numerical solution. Of course, we have to solve for delta naught trapezoidal for each beta, because delta naught equation 1 also has beta, right? So that's why I said first let's consider beta to be 5 degrees. Okay, then what we do is that, like, we essentially calculate the error between the two. Okay, let's say we call this as the absolute value between delta naught Ackermann, okay, minus delta naught trapezoid. Okay, you can even take a square error. Okay, I'm just taking the just absolute error, right? So I'm sure you can calculate this. Okay, so we do this, and then, like, we can essentially get a consolidated error for a given beta. Okay, so once we essentially calculate this array for a given beta, so E delta naught for a given beta can be calculated from this column. Let's say we want to calculate the mean square error, right? It's going to be equal to square root mean error, right? So essentially we square each of these I entries, okay, and then we sum them, okay, we divide by n and take the square root, okay. So this we are going to get for every beta. All right, then increment beta by 1 degree till beta becomes equal to 30 degrees. Okay, and then repeat this process. Okay, go here, repeat this process. Okay, so form the same table. Of course, delta naught Ackermann, as I told, is a one-step process, right? Beta doesn't come into play. We need to calculate delta naught trapezoidal and E delta naught, okay, for every beta, okay, and this consolidated measure E delta naught beta, okay. Then what we need to do is the following. Okay, so we essentially then we'll have a series of values for this E delta naught beta as a function of beta. So E delta naught beta as a function of beta. So then what we do is the following. We essentially plot this for every beta, right? All the way, let's say, till 30 degrees, right? And let's say we plot them, okay, we have calculated. So let's say for 5 degrees it's here, 6 degrees it's here, 7 it's here, 8 is here, and so on, right? And then somewhere here, we reach the minimum, okay? This, okay? Somewhere here is where we reach the minimum value, okay? This beta is our answer, okay? So this is the beta where we reach the minimum value as far as this particular metric is concerned. What is this metric? This is the mean square error, right? So it is at this point I essentially reach the minimum value. So the best value of beta, which we call as beta optimum, is the argument over all range of beta, which minimizes this metric E delta naught beta, okay, that we have calculated. So what does this formula mean? That means that we have beta going from 5 to 30, right? So we essentially calculate beta in discrete increments, and then like we figure out which is the value of beta at which that number, right, or that metric becomes the least value, right? And then like we take that as the best value of beta. Okay, so that's one way to calculate the value of beta that will essentially give me the best possible result, right, as far as the trapezoidal steering mechanism is concerned. Okay, so I hope it is clear, right? So of course, in this example, the value of n is 40, right? So we essentially have 40 angles for delta I. Of course, if you increment in 0.5 degrees, the value of n will be 80. Okay, you will have 80 data points in the state, right? So those are things which I'm sure are pretty straightforward to understand, right? So just to repeat the process, like once again, like we are looking for designing this trapezoidal steering mechanism that will give us the best possible result. So what we are doing is that like we want to figure out what will be the value of beta, which will get me the best result, right? So in order to do that, we essentially are going to solve for this beta that minimizes a performance metric or an error index. And that's the process we have figured out, right? So we fix beta at some value initially. We calculate this metric. So what is this metric? This metric sorts of quantifies the error between what the trapezoidal steering mechanism condition will give me and the Ackermann steering condition will give, right? So that will be the metric, and that is used to essentially obtain a plot between this error metric and beta, and then we choose beta as the best as a value which essentially minimizes this. Okay, so that's what we have. All right. So this is an optional numerical exercise once again. Okay, so please do try out, and if you have any questions, please do ask me later. Okay, once you have started the coding. So any doubts on this process? So please do try out, okay, like using the numerical tool that you are familiar with, and then like I'm sure it will be a good exercise for you, right? Fine. Okay. So having looked at this bicycle model, I'm going to introduce two other models in this particular course. Both models, like belong to what is called as the well-known bicycle model. Okay, so I'm sure this is a term which all of us will encounter whenever we study steering dynamics or cornering dynamics in the context of road vehicles. So essentially, one can also call it as a single track model. Okay, so let me explain why it is called so and what this is short. Okay, so as we recall, the scope of this course is on four-wheeled single unit vehicles. Right? So if I consider a four-wheel vehicle, we are going to consider, let's say, drawing a simple schematic. So for the vehicle, so let's say I draw wheels. Okay, so I am essentially connecting the four wheels, and then like we are going to have two tracks. Okay, so a left track and a right track. Okay, so let me just draw these four wheels. So without loss of generality, let's say this is our 4-wheel. Okay. So now what we do is that, like, when you consider our bicycle, we essentially combine this left wheel and the right wheel as one wheel. Okay. And on the front, and we do the same process on the rear. Okay, so we combine the left wheel and the right wheel on the rear as well, and then we join them together. Okay, so we join them together. Is happening. Okay, so this is what we do. Okay, when we want to essentially go for this bicycle, right? So we essentially go from 4 wheels to 2 wheels. Okay, so that's why it's called as a single track model or a bicycle. Okay, so we are going to combine the 2 front wheels and the 2 rear wheels together. Okay, so that, like, we have the single track. Okay, so they are useful for studying cornering dynamics. Of course, one should immediately note that this is a very useful model for studying the yaw motion of the vehicle during cornering. But then, like, we cannot capture the roll motion, okay, during cornering using the single track model. Okay, so that is a limitation of single track or the bicycle. And if we look at this bicycle model, okay, we can in fact once again have 2 submodels that we are going to see. Okay, so what are these 2 submodels? Okay, the first one, sorry, some problem. Okay, sorry about that. I think suddenly screen sharing got stopped. Okay, I hope now it is visible. Okay, so essentially, if we look at the bicycle model, there are broadly 2 types of models, okay, that we are going to discuss. The first one is what is called as a kinematic bicycle model, which is typically used at low longitudinal speeds. Okay, so this is used at speeds till about less than about 5 meters per second. Okay, so that's just an indicator for us to sort of decide when to use it and when not to use it. Okay, so and at speeds above these values, we go to what is called as dynamic bicycle. Okay, so and as the name adjective kinematic and dynamic indicate, like we immediately get a feel of what these models will capture, right? So as we know, in kinematics, we are only going to be interested in modeling the motion without really looking at how the motion is caused, right? We don't worry about the forces, moments that cause the motion. Whereas in a dynamic model, we are typically interested in the cause of the motion, right? And the motion itself, right? So we will relate the forces, torques to the motion. Okay, so we will first get started with the kinematic bicycle model, and then, like, we will learn the dynamic bicycle. Okay, so that is going to be our plan of action. Okay, so let me first introduce what this kinematic bicycle model is, and then, like, we will derive the equations also subsequently. Okay, so I hope it is clear what is meant by a bicycle model to begin with, and then what is this kinematic bicycle model and what is this dynamic bicycle. Okay, so we'll do each one one by one. Okay, so first, sorry, what is this? Sorry about that. Just give me 1 second. So let me just copy this image. Here. Okay. So now, if we look at this image, this is a very simple schematic just for us to learn and understand what we are going to deal with when we are dealing with so-called kinematic bicycle. Okay. So, in fact, later on, we will realize that when we deal with the kinematic bicycle model, we are going to neglect what is called as slip angle, okay, which is essentially tap on the lateral direction. To that, I will define what is slip angle and what is its importance and so on later on. But at this point in time, I have to state that when we essentially deal with the kinematic bicycle model, we are going to neglect tire slip in the lateral direction. Okay, that's an assumption behind this, and that's a reasonable assumption. Yeah, the range of speeds, that we are considering, right, which is less than 5 meters per second. This is a reasonably, say, accurate assumption to deal. Okay, so we are essentially going to neglect what is called a slip angle. Okay, I will define what the slip angle is and what is its importance later on. Okay, when we deal with the dynamic bicycle. Okay, so let me identify important components of this say kinematic bicycle model. Okay, so here if you look at this 2 points A and B. Okay, so we can see that point A is the center point of the two front wheels combined together, and point B is the center point of the two rear wheels combined. Okay, so this point A is indicated front of the vehicle. Okay, point B is indicator of the rear of the vehicle. Okay. And if you look at the line segment AB, this in a certain sense sort of like lumps the vehicle, okay, along with longitudinal axis. Okay, so essentially in this model, we are visualizing the vehicle as this lumped line segment, okay, AB. Okay, C is the center of gravity of the vehicle. Okay, so C is the CG of the vehicle center of gravity. Okay, so the wheelbase of the vehicle is going to be capital L, and we are going to use what are called LF and LR to denote the longitudinal position of the CG with respect to the front wheel and the rear wheel center. Okay, so the wheelbase of the vehicle, which you know is the distance between the front wheel center and the rear wheel center along the longitudinal axis, is going to be this LR. Okay, this is capital L. Capital L is the wheelbase. Okay, and what is LF and LR? LF is going to be the distance between the front wheel center and the center of gravity. Shift. So I hope we can understand what is, right. So this is the front wheel center A, and the distance AC is essentially, we call it as LF. Okay, and this distance from the rear wheel center B to this point C is what we call as LR. Okay, L sub. So obviously LF plus LR is going to be equal to capital L. Okay, so that is something which we can immediately realize. Okay, so we can immediately see that there is an axis XY. What is this axis? Axis XY indicates an Earth fixed coordinate system. Okay, so axis XY is an Earth fixed coordinate system. Okay, and essentially the coordinates of the CG, okay, are going to be indicated by some capital X, capital Y. Okay, so that's what it is, right? So if you look at the coordinates of the center of gravity with respect to this origin O, okay, they are going to be some capital X, capital Y. Okay, so that's what we are going to have. All right. Okay. Now, a few more variables for us to define. Okay, so let's say V is the magnitude of the velocity vector V is the vehicle speed. Okay, so V indicates the vehicle speed, Okay, and let's say the vehicle speed vector at the center of gravity is at an angle of beta with the longitudinal axis of the vehicle. So this angle beta is what is called as a side slip. So this is what is called as a vehicle side slip. All right. So shortly discuss this in more detail. Okay. So beta is what is called the side slip. Okay. So then delta F, okay, is the steering angle of the front wheel. Okay. So delta F is the front wheel steering angle. Okay, as indicated here, this figure. And delta R is the rear wheel steering. So at this point, we are essentially considering that both front wheel and rear wheel are steered. Okay, so but of course, if we have only pure front wheel steering, we take delta R to be 0. Okay, that's quite straightforward. I'm sure that is understood, right? So if we don't have the rear wheels to be steered, delta R will become 0. All right. Okay. So these are some important parameters in this. Of course, I should introduce also this parameter psi, which you can see here. Psi is this parameter. So what is a psi? Okay, psi is nothing but what is called as the heading or the yaw, okay, or the orientation angle. Okay, so we can observe that psi is the angle made by the longitudinal axis of the vehicle XY, sorry, AB, with the capital X axis. Okay, so that is what is called as the heading of the yaw angle. Okay, and variables X, Y, and psi. Okay, completely characterize the vehicle state. Okay, as far as the kinematic bicycle model is concerned. Okay, so if we are able to get evolution equation for these three variables, we are done. Okay, so essentially, if we are able to get equations that characterize the evolution of x, y, and psi, we will be able to get we'll be able to characterize the bicycle model, or to be very precise, the kinematic bicycle model. Okay, so these are the various variables involved in the kinematic bicycle model. Okay. Now, okay, before I go and add a few more terms in this figure, are there any queries before we go ahead? Fine. So now let's look at this instantaneous center of turn and so on. Okay, so let's look at it. Okay, so suppose let's say I draw a line which is perpendicular to the front wheel. Sorry, the central plane of the front wheel. Okay, and I draw a line which is perpendicular to the central plane of the rear wheel. Both of them intersect at this point O, which is the instantaneous center of turn. Okay, so this point O is the instantaneous center of turn. Okay, so that's the instantaneous center of turn. Now we draw a line segment from point O to point C, which is the CG. Okay, that is going to be the turning radius. Okay, so this is the R. Okay, the parameter R is going to be the turning radius. Okay, and the velocity vector of the CG is going to be perpendicular to the the line segment OC. Okay, so that's why we get this side slip angle beta. Okay, because you can immediately see that the velocity vector at the CG is going to be perpendicular to the line segment OC. Okay, because we are not considering slip along the lateral direction. And we can immediately observe that that is not going to be aligned with the longitudinal axis of the vehicle, which is AB. So the angle between the velocity vector at the center of gravity and the line segment AB, which is representative of the longitudinal axis of the vehicle, is this angle beta, okay, which is what is called as a side slip angle. Okay, I hope it is clear how we got the side slip angle. All right, okay. Now, let's go and identify some more variables or like some more parameters in this particular uh, diagram. Okay, so let's start with this, right? So first we know that this angle is delta r. So immediately we can immediately figure out that this angle is going to be pi by 2 plus delta r. Why? What angle are we talking about? We are talking about the angle CBO. Okay, the angle CBO is immediately 90 degrees plus delta r, right? So that is something which all of us can figure it out, right? So that's pretty straightforward. Okay. Then if we go to the front wheel, okay, so this angle is going to be delta f. Okay, we know that. All right. Now, if we, sorry, this angle is going to be pi by 2. Then how did we get this pi by 2 minus delta f? We essentially make use of the fact that this is a straight line. Okay. So the angle CAO or OAC, okay, is going to be pi, because pi will be the sum of the three angles, minus pi by 2 plus delta f. Okay, so that gives us pi by 2 plus pi by 2 minus delta f. Okay, so I hope it's clear how we got this pi by 2 minus delta f. All right. Okay. So I hope that is clear to all of us. Now, let's say we fix a local coordinate frame, okay, to the vehicle body, okay, and we call this axis as axis small x. Okay, what is this? What is this axis small x? The axis small x is along the, what happened? Sorry. Yeah, the axis small x is going to be along the wheelbase, right? So along the line segment AB. And we essentially take an axis small y. This is going to be perpendicular to this axis small x. Okay, that's going to be the local coordinate frame. Okay, small x, small y indicates the body fixed frame of reference. Okay, so small x, small y is the vehicle fixed frame of reference. All right. So the CG, like we can observe that we are going to have the side slip angle to be this angle beta, and we have other angles at play also. Okay, so let's see what these other angles are. Okay, small x, small y is the vehicle fixed frame of reference. We can immediately observe that this angle, let me mark it carefully. This angle, what do I mean by this angle? Okay, is going to be equal to pi by 2 plus b. Okay, so I'm sure all of us can figure it out. So the angle ACO or OCA is going to be pi by 2 plus beta. Okay, so we have a right angle and then we have an additional angle which is pi by 2. All right, so that is also something which is clear to us. Now, having established all these things, we can immediately get expressions for these two angles, right? How do I get this angle as delta f minus beta? That's pretty straightforward, right? We take the triangle OAC, right? As we know, the three angles of a triangle must sum to 180 degrees or pi radians, right? So this angle AOC is going to be pi minus the first angle is pi by 2 minus delta f, okay, which is one angle. And then another angle is pi by 2 plus beta. Okay, so if we evaluate this, if we simplify this, we get delta f minus beta. Okay, so I am sure that is straightforward. Similarly, if we consider the triangle OBC, we have this angle to be beta minus delta r, right? How did we get this? Same logic. The three angles of the triangle must sum to pi radians or 180 degrees. So angle BOC is going to be equal to pi minus pi by 2 plus delta r, which is pi by 2 plus delta r is one angle. And then this angle, which is going to be equal to pi by 2 minus beta. Which angle is pi by 2 minus beta? This angle. Okay, sorry. This angle is, sorry, oops. This angle is going to be pi by 2 minus beta. How did I get the pi by 2 minus beta? This angle is pi by 2 plus beta. This angle should be pi by 2 minus beta. One, right? Only then they will sum to pi. Okay, that's a straight line that we have, right? So that is what. So if we evaluate it, we get beta minus delta R. Okay, so I'm going to leave with this statement. So, and then like which we will derive the corresponding equations in the next class. So having established all these parameters in the figure, so what does the kinematic bicycle model do? It provides us with equations that characterize the evolution of x, y, and psi with time. Okay, when the inputs given to it are delta f and delta r. Okay, so delta f and delta r are the inputs to the kinematic bicycle model. We want to have an evolution equation for x, y, and z. Okay, so we learn how to derive that equation in the next class. Okay, so this is a good place for me to stop. So are there any questions before I stop the recording?
Sir, you mentioned that there is no lateral slip, right? Again,
Yes,
you're
yes.
considering side slip angle.
Side slip angle means, it is, although the term side slip angle has the word slip, okay, it is not a slip angle, all right? So it is a good point. It is just the terminology given to the angle beta, okay? Yeah.
Okay, okay.
So it just indicates that, like when there is no slip, the velocity vector is perpendicular to OC, and that doesn't align with AB, okay? So that is called as beta, and that is conventionally called side slip. Okay, good question. Okay, so that doesn't mean, although by terminology, although it has the word slip into it, it is not reflective of the slip angle. Okay, yeah.
Okay, sir. Thank you.
Right. So let me stop recording, and then we'll continue in tomorrow's class. Thank you.